Before we begin tearing down the 13B core, let's look at the minimum required tools to complete this task. For wrenches, you will need a 19, a 17, a 14, a 12, and a 10 millimeter. 3/8 drive shallow sockets, a 10, a 12, a 14, and a 17 millimeter. 3/8 drive deep well sockets, a 10, a 12, and a 14 millimeter. 1/2 inch drive deep well sockets, a 17 and a 19 millimeter. You will also need this special socket, a 54 millimeter socket. This is used for removing the flywheel nut. If you cannot find a 54 millimeter socket, a 2 1/8 inch diameter socket will work as well. You will need a long handled 3/8 drive ratchet, a short extension, and a long extension. You will also need a 1/2 inch breaker bar at least 24 inches long. Some other tools that are required for disassembling the 13B are a dead blow hammer or a plastic faced mallet, a pair of electrician's dikes, a pair of needle nose pliers, a pair of side cutters, an 1.5 inch wide stiff bladed putty knife, some electrician's tape, a T-puller for removing either the flywheel or the rear counterweight. Although not specifically required, if you have access to air tools, they will be highly beneficial in disassembling the 13B Rotary. If you're going to be using hand tools to disassemble the Rotary, you'll need to construct a locking bar as I have here. The locking bar is used to bolt against the flywheel and lock the eccentric shaft in place when you break loose the rear eccentric shaft nut and the front eccentric shaft bolt. Let's begin the engine disassembly by removing pulleys, any extra bracketry, and if you still have your air pump or alternator, remove those as well. Remove the oil injection lines at the pump and swing them behind the water pump intake pipe. There is a water hose and a sensor that must be disconnected behind the water pump housing. Remove the 4 nuts and lock washers retaining the pump and housing. Strike it with a dead blow hammer to release the gasket and slide the assembly off. This rod connects the metering pump to the throttle body. Handle it with care and avoid bending it. Remove the cotter pin and washer and disconnect the rod from the throttle body. Now repeat this process at the metering pump. Tape the washers and pins to the shaft and store it. Remove the retaining nut and then remove the crank angle sensor. To remove the upper plenum, there are several vacuum hoses, water hoses, and electrical connections that must be disconnected. Refer to the Haynes manual on page 78 for more detail. There are several bolts that help support the upper section of the intake. Don't forget the 2 hidden behind the air bypass solenoid. Disconnect the secondary injectors and fuel lines. Now remove the 1 bolt and 4 nuts at the upper intake flange. Strike the intake with a dead blow hammer to release the gasket. and pull it straight up. Remove the vacuum lines, lower injectors, and wiring harness as a unit. There are a few hose connections at the oil filler tube as well as the temperature sender that need to be disconnected back here. You will need a thin 14mm wrench to remove the oil injectors. Do not try to use a pair of pliers on the smooth ends. To gain access to the lower intake studs, you must remove the two secondary actuator motors. Remove the remaining bolts and then the lower intake. Removal of the exhaust manifold is a simple matter of removing the four retaining nuts. Remove the passenger motor mount leg and all of the pan bolts. All right, to release the oil pan, you're going to need a dead blow hammer and a thick bladed putty knife. Go ahead and strike the oil pan several times away from the sensors. Try to loosen it up. Then come in from an angle, preferably over one of the iron housings. Then tap it. Remove the oil strainer. Followed by the front pressure regulator cap, spring, and piston. If you don't have access to air tools, now I'm going to cover how to remove the front hub bolt and the rear flywheel nut by hand. Before you break any of the fasteners free, you need to attach a locking bar to the flywheel. This is a piece of aluminum angle that's been drilled to match the bolt pattern for the pressure plate and bolted in two places on the flywheel. The first fastener that you want to break free is the front flange bolt. Even though it's torqued to only a third of the torque that the rear flywheel nut is, it has more contact surface area and is installed with quite a bit of blue Loctite, so it normally gives the most resistance. Take a 19mm socket and at least a 24-inch half-inch drive breaker bar. I normally step on top of the engine to hold it in place while I do this. And if you bounce on it a little bit, it'll normally break free. Only turn the bolt about 1/4 inch. We do not want to remove it until we're ready to take the front cover off. Once you have broken the eccentric shaft front flange bolt loose, get your 2 1/8 or 54 millimeter socket, a half-inch drive breaker bar at least 24 inches long, and we'll move to the flywheel nut. I normally stand on the locking bar with one foot and stand on the engine with another. Get in position, and if you bounce on the breaker bar lightly, it'll normally break free. Sometimes the socket will pop off, so I may want to put an arm down here. And that's it, just a quick break. You can go ahead and take this nut off. With the engine sitting front up, remove the front eccentric shaft bolt. Remove the bypass thermostat and spring. And remove the 6 front cover bolts. And then finally the front hub. Tap on the front cover with a dead blow hammer to loosen it. Now slide off the accessory gear. Before removing the oil pump drive chain, you want to inspect the amount of slack the chain has in it. The easiest way to do this is find a link on one side of the chain that's equal distance between the two shafts. Push it in with your finger as far as you can go. Now take a measuring tape or rule and measure directly across the chain. This distance is 3 inches. Take that same length and push it out as far as you can. And measure again directly across the chain. This distance is 3.5 inches. The difference between the two measurements is the actual amount of slack you have in the chain. In this case, this chain has 1/2 inch of slack, which is too much. 3/8 of an inch slack is about the limit on these chains, so this chain needs to be replaced. Take a chisel and a hammer and flatten the lock washer below the oil pump nut. Remove the oil pump nut and then remove the drive sprockets and chain together. Slide the front counterweight off the shaft. Remove the front thrust washer and inspect it for any obvious wear. Remove the front thrust bearing, then the front key. Now remove the 6 stationary gear bolts. Set one aside for a later use. Remove the center plate and inspect it for wear. Now remove the selective spacer. Note the letter etched on its side. This is a V spacer. Slide up the rear thrust bearing and remove the rear thrust washer and inspect it. Now take that one stationary bolt and replace it in one of the holes, finger tight. This will hold the stationary gear in place during the rest of the disassembly. Remove the oil pump bolts and the oil pump. Now, here's the easy way to remove a flywheel nut. One, when using a puller to remove the flywheel, make sure that the tip is not going to enter the back of the eccentric shaft, especially if it's a manual transmission. You could damage the pilot bearing. I always use a type of bushing to keep that from happening. Go ahead and take an impact wrench and tighten up your puller. Then take a hammer and tap it lightly on the outer edges. And your flywheel should release. After removing the flywheel, take out the flywheel key. Then, take some electrical tape and wrap it around the threads of the eccentric shaft. The reason we do this is not only to protect the threads, but also to protect the main bearing in the rear stationary gear as you draw it across the top of the eccentric shaft, or the back of the eccentric shaft. Now remove the 6 retaining bolts for the rear stationary gear. Now I like to use a seal puller to remove the rear stationary gear. You can use 2 screwdrivers just as easily. Pry on it, and then gently lift it straight up. Regardless of whether or not you're using air tools, you need to break the tension bolts free with a breaker bar and a 17mm socket. Turn them about 1 to 1.5 turns and break them free in a crisscross pattern. Once you've broken free all of the tension bolts, then you can use air to run them out the rest of the way. Once all the tension bolts have been unscrewed, just simply draw them out. Remember not to forget the ones on the side down near the oil pan. To remove the rear housing, once you have all of your tension bolts out, just simply take a dead blow hammer, find an edge, and tap up until the O-rings release. And then just pull straight up with it. 1. Now remove your dowel pins that are at 11 and 5 o'clock. Use a tension bolt, slide it in, pull it to the side a little bit, then pull straight out. The removal of the rotor housing is identical to the rear end housing. Just simply take your rubber mallet, tap until you feel the O-rings release. And pull straight up and out of the way. Now we have a rotor to remove. To keep the parts on the bottom side of the rotor from sticking to the center housing or the intermediate housing, I normally work the rotor back and forth a little bit. You're going to want to come straight up. You'll almost always lose the rotor oil seal. Come straight up over the eccentric shaft and then flip it vertical, like that.
Now for the center housing. To remove the center housing, we have to raise the eccentric shaft up about 1 inch. And this normally requires the help of a partner. A couple of things that you need to do to set up for removing the center housing. First of all, take the eccentric shaft lobe and rotate it so that it's in line with the intake port. That'll facilitate an easier rock over the eccentric shaft lobe because we're going to be flipping it like this and up. Now again, take a tension bolt and remove 2 more dowel pins at 11 and 5 o'clock. Take your rubber mallet or dead blow mallet, tap on the housing till the O-rings release.
Has this got voice on it too?
Yes, it does.
Cool.
All right. Go ahead and you lift the eccentric shaft about 1 inch. Right about there. And I'm going to rock over, and then you let yours back down. Guess what, genius? Now to remove the front rotor housing. Same game. Tap on it till the O-rings release. Then just lift it straight up. That's it. Now we'll remove the eccentric shaft. We'll simply pull straight up with it. Set this up. Rotate it around again. And then just rotate it straight up. Now for the main stationary gear, simply remove that 1 bolt that you put in by hand. That one. And slide it out.
Cleaning and inspection. This is the most important stage of the overhaul. Attention to detail is very important. Each part will be covered in a session that will include both cleaning and inspections. Examples of common failures will be given when possible. It's assumed the viewer will track the location of identical parts such as rotors and rotor seals. When measurements are taken, they should be recorded for later evaluation. For example, computing the running clearances of neighboring parts. Understand that only one example will be given for multiples of the same part. The viewer is expected to repeat the same procedure with the remaining components.
This is an industrial parts washer. It uses mineral spirits as a solvent. If you don't have access to one of these, then a large pan and mineral spirits available from the hardware store will work just as well. This is the chemical that we use for decarburizing parts. The container on the left is an industrial grade cleaner and is probably difficult to get if you're an individual. You can buy the gallon size carburetor cleaner at most auto parts stores. Make sure that it is aluminum and Babbitt safe, and always use chemically resistant gloves when working with these.
If you have access to a utility sink, I always recommend a hot soapy water wash as a final procedure for cleaning cast and porous parts.
Here are some of the materials that you'll need for cleaning 13B parts. You'll need a parts washer brush, a brass bristle brush, an old toothbrush, a thick-bladed putty knife, 2 cheap standard screwdrivers, an X-Acto knife, a utility knife blade, an old Apex seal, some side seals, a pair of rubber gloves, some oven cleaner, household oven cleaner, carburetor and choke cleaner, some dishwashing detergent, a scouring pad, and a rubber block with some 400 wet or dry sandpaper.
Begin the cleaning process by scrubbing all the parts with the exception of the rotors in the parts washer.
After a thorough scrubbing in the parts washer, these components are now ready for inspection. They include the front eccentric shaft bolt, the oil bypass thermostat, the pulley flange, the front cover, the accessory drive gear, the oil pump and drive gears and chain, the front counterweight, the thrust washers and bearings, both stationary gears, the oil pan, the oil pickup tube, all small fasteners, and the dowel pins.
We'll begin with the thrust washers and bearings. Visually inspect them under a magnifying glass if possible for any visible wear, such as pitting, grooving, and scratches. The polish marks where the bearings ride on the thrust washers are considered normal. The actual condition of these parts will become evident when they are installed and the end play is checked. Out-of-range end play measurements ranging between 1 and 3 thousandths normally indicate that the needles in the bearings have worn. In this case, it's more desirable to replace just the bearings than compensate with a shorter shim. Oil pump inspection. First of all, you need to disassemble the oil pump to inspect it, so remove the set screw with a small screwdriver. Now we're going to dump out the rear outer rotor. Now you'll notice that this rear outer rotor has a mark on it that always faces the open end of the pump. Now we're going to remove the main shaft. The main shaft contains the 2 inner rotors and a spacer. Set that out of the way for the moment. Now we're going to remove the front outer rotor. It as well has a dot that faces the open end of the oil pump. Now take the front outer rotor, place it on its corresponding inner rotor, and check the clearances between the 2 lobes. This should not exceed 8 thousandths of an inch. Take the front outer rotor again, slide it into the housing, and check the clearance between the outer rotor and the housing. This should not exceed more than 8 thousandths of an inch. Now we're going to reassemble it with the dot facing the open end. Slide the front outer rotor into the housing. Take the main shaft and slide it into the housing. Now the spacer on the main shaft has a slot in it. This slot has to be rotated around and lined up with the set screw hole. Push it in, rotate the shaft slightly to get it to engage the outer rotor and push it in. Now take your set screw and apply red Loctite to it and screw it all the way down. I found more than one of these set screws in the bottom of an oil pan. I also take a punch and peen the aluminum around the set screw to ensure that this will not come out. Now take your rear outer rotor, slide it in place, and check the clearance between the 2 lobes here. This again should be no more than 8 thousandths of an inch. Check the clearance between the outer rotor and the housing, no more than 8 thousandths of an inch. Now we're going to set it up to check the clearance between the gears and the housing itself. So put a straight edge on top and slide a feeler gauge between the gears and the straight edge. This should not exceed 19 thousandths of an inch. And this concludes the inspection for the oil pump.
Front pressure regulator inspection. First of all, inspect the piston for any deep gouging, something that you could catch your fingernail on or embedded dirt. It will be slightly scuffed and that's normal. Now take a magnet and stick it inside of the piston. Slide the piston into its bore. Shuffle the piston back and forth several times in the bore to ensure it doesn't stick or bind. If it moves smoothly in the bore, then you can consider it ready for use. Rear pressure regulator inspection. Look through the discharge ports at the piston. Look for any scratching, gouging, or dirt. Now turn the pressure regulator upside down and place a screwdriver on top of the piston. Push the piston up and down and allow it to return on its own several times. If this action is consistently smooth, you can consider the rear pressure regulator good. Next are the tension bolts. While washing the tension bolts, remove the sealing washers and discard them. Then, wire brush both the threads and the bolt heads.
Once you've finished cleaning the tension bolts on a wire wheel brush, get a 10 by 1 millimeter pitch die, spray a little WD-40 on them, put that die, make sure you don't get cross-threaded. Run it down about a 1/4 inch sticking out, and come back. You don't need to chase the threads all the way down on these things. I don't know why the threads are so long. The threads only go in about 3/4 of an inch on the front housing. And that's it. Now it's time to move on to the more complicated parts. Consequently, they require more than a set of feeler gauges to inspect. Here are the basic tools needed. You'll need a set of 0 through 4 inch micrometers, a 1.5 through 2 and a 2.5 through 3 telescoping gauges, a pair of dial calipers, a dial indicator on a magnetic base, a set of feeler gauges, a machinist's rule, and a magnifying glass. Now let's take a look at the stationary gears. Begin inspection of the stationary gear by looking at the teeth. We're looking for chipping, gouging, or general excessive wear. Inspect the bearing surface for any significant wear or damage. This line of missing babbitt down the center of the bearing is actually produced by the manufacturing process. The bearing starts out as a flat piece of steel. It's rolled into a cylinder and fastened together by a puzzle joint. This puzzle joint is then ground slightly by Mazda to reduce any high points. Again, this is normal, and you'll find the same type of joint in the rotor bearings. Now we're going to mic the main bearing. First of all, we're going to look at it as a 2-piece bearing divided by the oil groove. We're going to measure on top. We'll measure across and then 90 degrees to that. Then we'll flip it over and measure across here and then 90 degrees to that again. And of course we'll be writing these figures down. I take that, mic it. I'll take this and mic it. And mic across this way and across that way. Now you want to use your largest figure to calculate your oil clearance after you've measured your eccentric shaft. And the cleaning and inspection of the eccentric shaft by mounting it on a pair of V-blocks so that you can suspend it off the table. The first thing we're going to do is remove the oil jets. You've got one there and you've got one here. To remove the oil jet, get a very large bladed screwdriver and simply unscrew it. There's the jet. Now get a magnet and remove the spring, and then reach in and retrieve the check ball. Flip the eccentric shaft over and inspect the threads. They can be repaired with a file if necessary. Now inspect your pilot bearing. If it's bad, this is a good time to replace it. Now rinse off the eccentric shaft very carefully and use compressed air to blow everything dry. Make sure that you blow compressed air in every oil hole. Now visually inspect the eccentric shaft for any types of scratches or scarring. Anything that you can catch your fingernail on is something to be of concern. Mic the eccentric shaft lobes and journals by dividing them in half lengthwise by the oil hole and measure in 2 spots. Then rotate the eccentric shaft 90 degrees and measure again. Normally, a good eccentric shaft will not vary more than 3/10 of a thousandth of an inch. And calculate your oil clearance using the smallest measurement found on that particular journal. Now let's turn our attention to the side and intermediate housings. Scrub them thoroughly in the parts washer. Use a brush to get some of the baked on grime loose. And of course we have gaskets that need to be scraped. I use a thick bladed putty knife that's been sharpened. Now these are two specially ground screwdrivers. One fits each O-ring groove. Take a screwdriver and dig out the O-rings. The combustion O-ring has two liners and then the rubber center section. Make sure you get out the liners. Now the outer water jacket O-ring is just one solid piece of rubber, and it's normally easy to dig out in one piece. Now take your screwdrivers and scrape the O-ring grooves thoroughly. You'll be surprised how much trash you'll lift out of these O-ring grooves. There's a piece of a liner coming off now. That liner's made out of Teflon, I believe. Normally takes about 30 minutes to scrape each housing face. Now take a utility blade and scrape the water jacket area, holding it nearly perpendicular to the surface. Pull off any residue that's on the water jacket area. There's some of the trash I took off. Now take a green scratch pad, a Scotch-Brite pad, and scrub around the water jacket area. Now if you have access to air tools, an air grinder with a Scotch-Brite disc works wonderful for cleaning up this area. For baked on grease and grime, household oven cleaner works great. Just simply spray it on. And then take a stiff bristled brush and work it into the greasy spots. Let it sit for about 2 hours and then wash it off in hot soapy water. Once you're done, blow it off and get it completely dry. You don't want any standing water on it. Then re-scrape your grooves.
To chase out the bolt holes in the front, intermediate, and rear housings, you're going to need 4 specific taps. These 3 are bottoming taps, which just basically means the tip has been ground off. This is a 6x1, and it's used for the oil pump and the oil pump pickup. This is an 8x1.25, and it's used for the stationary gears, the front cover, the intake bolt holes, and other miscellaneous holes. This is a 10x1, and this is used for your tension bolt holes. And then you'll need a 10x1.25, and that's for the bell housing bolt holes. This does not necessarily need to be a bottoming tap because all but one of the bolt holes go all the way through. Take a little bit of WD-40, spray it down in each hole. Take the bottoming tap, start it, and chase out your tension bolt holes. This is very important to give you an accurate torque on your tension bolts.
Now go ahead and chase out all of the other threads in your housings.
One of the first things you want to check the end and intermediate housings for is surface rust on the machine face. Surface rust can normally destroy one of these housings because the pitting goes down below the surface. You'll almost always find black spotting on the surface, and I believe that's from the nitriding process or the hardening process of the machine surface. But any large pockets of rust, take a green scratch pad or a brass wire brush and work them down and make sure that they don't pit deeply into the surface of the housing. Here's another example of what surface rust can do to an end housing or intermediate housing. Once it's cleaned up, you'll find that your surface has pits in it. And this one I can actually catch them with the tip of a screwdriver. And also, down in this area, the surface is very porous, which is going to accelerate the wear of your rotor oil seals and side seals. So this housing has to be either lapped or replaced. This is the outer wall of the combustion O-ring groove on the front housing, down near the exhaust port. And notice how thin it is. A lot of castings are this way, and Mazda's had some trouble with this outer wall breaking off and falling into the water jacket. And then, of course, the O-ring is pushed into the water jacket, and the car exhibits symptoms of a blown head gasket. In other words, you'll have pressurizing of the coolant system, you'll be burning coolant, and there's really no fix for it other than replacing the entire housing. This one is about as thin as I'd like them to get. And the thickness of this wall right here is about 61 thousandths of an inch. If they're thinner than that and they haven't failed, you might want to build them up with some epoxy. It may not be worth purchasing new housings just if they're very, very thin, and where some epoxy buildup can help secure that wall. But if they've already cracked or chipped off, I would highly recommend going ahead and getting another housing. The first real measurement inspection that you'll need to do will be to check the housing flatness, and we do that with a straight edge and a 1.5 thousandths feeler gauge. It's a very simple test. You simply slip your feeler gauge under the straight edge, make sure your straight edge is flat on the surface, and pull. If it moves the straight edge, then that area is flat. Okay, we're going to check it on all 4 sides. And this housing passes with flying colors. It's within limits as far as flatness. To test for side seal and corner seal stepped wear, take your dial indicator gauge, note it's 0, and begin sliding it across the step. Normally, the most wear is going to occur right in the center, right about right here. And this side housing has almost 3 thousandths of a step at the highest point, which is still within tolerance. The tolerance is 3.9 thousandths of an inch, or realistically 4 thousandths of an inch. Flip your dial indicator over, check the 0 again, and check the stepped wear along this side. And unfortunately, I can't show you the dial indicator on this one. And the step wear seems to be at maximum about 1/1000th of an inch. So that's fine. The other 2 step wear tests have to do with the rotor oil seals. And you've got 2, an inner and an outer tracing mark. The inner tracing mark is shaped like a football. All right, and its wear is going to, or the maximum wear is going to be close to the points of the football. Then you've got the outer tracing mark, which is a symmetrical circle. And I almost never get a reading on the outer tracing mark. But the inner tracing mark normally has some measurable wear near where the points of the football are. So we're going to take our dial indicator again and check the 0 on it. Oops. And rock back and forth across the maximum wear points. And I'm coming up with about 1/2 thousandth of step on that side. And maybe 1/4 thousandth step on this side. That's for the inner oil seal tracing, the football shaped tracing. And the limit on that is 0.8 thousandths or 8/10 of a thousandth, which this is within limits. Now, the outer tracing mark normally peaks again on the sides. And we're going to check that. That's less than a thousandth over there. Unfortunately, I'm going to turn my gauge around again so you can't see it. And this is less than half a thousandth over here. So front housing has passed all of its tests. It's passed its stepped wear test, its flatness test, O-ring wall integrity. So this will be a good housing to use in the rebuild. You're going to need to apply all of these tests to the other two housings, the intermediate and the other end housing. Cleaning of the outside of the rotor housing is straightforward. Simply take it to the parts washer and scrub. To clean the inside of the rotor housing, I recommend a 3M green scratch pad. And this is pretty good for getting any of the carbon off. That'll show up around the exhaust port and between the trailing and the leading spark plugs. To clean the side of the rotor housing, we need to remove all of this water jacket residue and also bits and pieces left from the O-rings. And the first thing I do is scrape the side with a utility knife blade. And you hold the blade perpendicular to the side and just moderate pressure. And simply scrape it clean. After scraping the rotor housing side, you'll notice that the area around the water jacket is still relatively dirty. So the next step in cleaning this up is to take a rubber sanding block with 400 grit wet or dry sandpaper. And we're going to lightly sand it in long, even strokes to clean it up. Keep the area lubricated and use long, even strokes. After sanding the rotor housing, you'll notice that we still have some rust-stained areas in the water jacket. Now, these are actually below the sealing surface of the O-rings, so you don't need to worry about them. The only way to remove this is to actually surface the rotor housing, and you don't want to do that because that's going to change the running clearance of the rotor inside the rotor housing. Now let's turn our attention to the area where the O-rings actually seal against the rotor housing. You're almost bound to find some light pitting in these areas. Now, if you're using an engine sealant such as Hylamar, this light pitting will have no effect on the O-ring's ability to seal against the rotor housing. If you do find some deep pitting, a quick fix is to take a wire brush and clean it out thoroughly, then take a razor blade and squeegee some JB Weld epoxy into the pitting. After it hardens, take your sanding block and sand it flush, and at that point it should be repaired. Rotor housing minimum width test. Now this is a test that's done on both new and used rotor housings. The idea is you inspect the inner edge of the rotor housing for any width variance. And if you determine that you have a narrower point than all the rest, you take the smallest measurement and you subtract from it your maximum width measurement from your rotors. And we'll get to that when we get to the rotor section. But what that'll give you is your rotor running clearance, and that needs to be about 10/1000ths of an inch. So what we're going to do is measure the rotor housing width in about 4 different spots. Take a set of dial calipers. And look for any width variance, recording the smallest measurement that you get. Now this is a brand new rotor housing, so I'm not reading any variance. But what you would do, this one came out to be 3.150. I would take that measurement and subtract from it my maximum width measurement on my rotor, and that would give me my rotor running clearance, which should be around 10 thousandths of an inch. Rotor housing final inspection. Here's what I'm sure we all want to have for our 13B overhaul. A set of new rotor housings, but at about $900 a pair, most of us would probably settle for some good used ones. If you follow Mazda's inspection criteria for rotor housings, you'll be hard-pressed to find a good set. Almost all used rotor housings will have some blemishes on the chrome surfaces, disqualifying them under Mazda's tolerances. The good news is that their criteria is very conservative. It's surprising to find what defects the 13B will tolerate, run well, and offer reasonable service life. So what I'll do is show you many of the common defects found in used rotor housings and give you my criteria for what is acceptable. Remember, these are recommendations and are outside of Mazda's criteria for good rotor housings. I'm only implying that I have had good success following these tolerances. Beveling on the edges is very common. This is acceptable if the taper of the bevel does not exceed 20 thousandths of an inch from its widest point to the edge of the rotor housing. Receding chrome is okay as long as it does not exceed 3/16 of an inch at the widest point. Use a Dremel tool to soften any jagged sections of receding chrome. Scratches at the exhaust port should be minimal and no more than 5 thousandths of an inch deep and 3/16 of an inch wide. The example scratch is too severe. Trailing plug scratches should be limited to 2 to 3 mild ones that are no longer than 1.5 inches long. This one is obviously too far gone. Grooving just inside the edge should not be deep enough to hook your fingernail on. A deep groove has a high possibility of ripping out an apex seal corner piece. Scratches or grooving between the leading plug and the exhaust port should be evaluated by the same standards as those found around the exhaust port. Check the exhaust port liners for damage or looseness. This one was severely overheated. They can be replaced by removing the roll pins on each side of the housing. Obviously, this one is a boat anchor. This is the damage caused by an apex seal being expelled from the engine. You can actually see pieces of apex seal embedded in the rotor housing. Before we break down the rotors for cleaning, if you did not identify the rotors as the front or rear when you tore down the engine, this is your last chance to do so. It's a very simple process. First of all, I always designate the faces of the rotor as either the gear side or the open side. Now, the front rotor is always going to have the corner section of the apex seal on the open side, and here it is. We've got the open side of the rotor, and here's the corner section of the apex seal. It looks kind of like a little triangle or boot. The rear rotor is going to have the corner section of the apex seal on the gear side, and there it is. So now we know if we had gotten them mixed up when we disassembled, this is the front rotor in the engine, and this is the rear rotor. Before removing parts from the rotor, take your drawing and label it as to which rotor you're working on. This is the front rotor. What face you're removing parts from. This is the open face. And then label your apexes. I always label them ABC, A, B, C in a clockwise fashion. So label your picture. Once you've labeled your drawing, go ahead and label your rotor. I'm going to take an F stamp, and anywhere along inside this perimeter on the inside of the side seals is fair game to mark a rotor because this is not a thrust surface. And you'll find out once you clean it that the Japanese engine builders have placed quite a few numbers on them and lettering. I'm going to label this as F, first of all, for front. I'm going to take an A, and this is going to be my A apex. I normally like to mark them on the flats. A, B, and a C. Now we're finally ready for disassembly. If the apex seals haven't already fallen out on their own, use a magnet to pull them out. The springs are not magnetic, so they will have to be pulled out with a pick. Be very gentle removing the rotor oil seals. The inner oil seal is rarely a problem, but the outer oil seal will often require some very gentle prying. As you remove the rotor oil seals, remove and discard the old O-rings. Now these are the oil seal springs. They need to be kept with the oil seals. Now I'm using an X-Acto blade, the flat side, and prying ever so gently and just a small bit at a time to work up the outer rotor oil seal. If you twist too hard, you can chip the sealing lip of the oil seal and destroy it. Now I'll warn you, never reuse the O-rings that are in these oil seals. They're very expensive, but they will cause you a lot of grief if you try to reuse them. They will not seal. Alright, pull the corner seals out with a magnet, and then come back with a pick to remove the corner seal spring. Be careful with the corner seal spring. They like to spring out and across the shop floor. Place the corner seal on a socket and use a drift to push out the rubber plugs. Discard the old rubber plugs. Now remove the side seals with a magnet. Then gently dig out the side seal springs with an X-Acto knife. If the side seal springs are being stubborn, you can gently scrape the carbon off the top of them, or you can leave them in the rotor through the first dipping to help soften the carbon. This is how I have been tracking my parts off camera.
On completion of disassembling the rotors, this is basically what you should end up with. You've got the front rotor gear side, the front rotor open side, the rear rotor gear side, and the rear rotor open side. Everything's separated. The only things that we're really not going to track are apex seal springs, corner seal springs, and side seal springs. They're not that critical that they go back in the same locations. In fact, I almost always recommend replacing the corner seal and side seal springs anyway, because they do flatten out over a period of time. You can pretty well successfully re-arc the apex seal springs. Now, first thing we're going to do is take our baby bottle, or little jar, that happens to be filled with carburetor cleaner, and I'm going to take my selection of springs and just drop them in there. I used to put them in a little basket and then drop them into the large can of parts cleaner, but sometimes they would slip through the holes, so I recommend dipping them in a separate bottle. Put the top on that, shake it up, set it aside.
This strange contraption is my own creation to separate rotor parts while they're being cleaned. It's made from safety wire, spring clips, and ring binders. The total cost is $3 for 4 of them.
Put it on. See. Put it on. I'm going to take these. This is what your parts hanger should look like when it's completely assembled. First of all, we have our corner seals. Corner seal A, B, C. Then side seals A to B, B to C, and C to A. We have our side seal springs on the last clip, and then our rotor oil seals tied at the ring at the bottom. Now you can just simply take this assembly and drop it into the parts cleaner.
Hang your parts in the parts cleaner for 12 to 24 hours. Afterwards, wash them in water, then dry and oil them. Take the rotors over to the parts washer and use a utility knife blade to scrape the carbon off the combustion sides. Hold the blade perpendicular to the surface. Now you'll need to use a brass brush to get into the pockets.
This will help them clean up faster in the parts carburetor cleaner. Once you've scraped all three sides, come back again, work them over with a brass brush. Pre-scrubbing the rotors dramatically improves the speed at which they're going to clean up in the parts cleaner.
Rinse the hollow sections thoroughly because they tend to hold a lot of oil.
And blow them dry with air. After scraping off the excess carbon and rinsing the rotor off in the parts washer, put a hanging wire on it. Make sure that your hanging wire runs underneath the rotor bearing, not over it. If you run over it, you could damage the soft babbitt. Now take your rotors and hang them in the parts cleaner for about 12 hours. This is what the rotor looks like after it's been dipped for approximately 12 hours in the carburetor cleaner and then taken out and rinsed off. At this point, it's time to scrape all the miscellaneous grooves in the rotor and remove all the carbon. Let's look at some tools that you can use for decarburizing the grooves of rotors. First of all, I have a 2-inch section of side seal that's had a point ground on each end. This is excellent for cleaning out side seal grooves. Then I have a top and bottom half of an apex seal that has had flats and points ground on them. They, of course, can be used for cleaning apex seal grooves and other areas on the rotors. Then I have an X-Acto knife, and the blade has had the tip ground blunt. This is good for cleaning side seal grooves and other areas on the rotor. Then I have a small screwdriver that's had the blade slightly sharpened, and this is excellent for cleaning out corner seal pockets. I'll begin by cleaning the side seal grooves. Now these side seal grooves still have the side seal springs in them because they were stuck in there with carbon when we were disassembling the rotor. At this point, you can either use your side seal spring tool that you made or an X-Acto blade. Slide it down into the groove and work it back and forth, digging the carbon out of the groove. The tool will normally glide over the spring and catch on the carbon. You can feel the carbon. Work it out. At this point, I should be able to lift the spring right on out. If you have removed any of the remaining side seal springs, take a can of aerosol carburetor cleaner and spray down into the groove. And that'll help soften up any of the carbon that remains. Go back through with your tool and continue to scrape it out. When you finish cleaning out the side seal grooves, turn your attention to the rotor oil seal grooves and area, and take a screwdriver, same procedure with carburetor cleaner, and work in this area and scrape out all of your carbon. Next in line are the corner seal pockets. Of course, take some carburetor cleaner, get them wet, and come in with your screwdriver. and scrape all of the carbon. With the sides of the rotors clean, I'm going to turn my attention to the apex seal grooves. And what I'm using is an apex seal that I've modified as a scraping tool. I've put a little bit of carburetor cleaner in the groove, and I'm simply going to scrape it clean. After I've decarburized all of the rotor grooves, I've got 2 steps left in the cleaning process. First of all, I'm going to return it to the carburetor cleaner for a couple of hours to remove any remaining carbon residue. Then I'll give it a hot, soapy water bath to remove any oil residue. At that point, it should be ready for inspection. After the rotor is thoroughly clean, now it's time to inspect it. The first thing you want to do is look for obvious damage, especially on the thrust surfaces. Make sure there are no dings, dents, or burrs on the stationary gear thrust surface or on the open side thrust surface. Check out the apex seal grooves. Make sure there are no burrs there. And look at the faces. Make sure there's no damage there. Next inspection is measuring the rotor width at the thrust surfaces. The 2 thrust surfaces on the rotor are the flat spot on the stationary gear and the large inner ring on the open side. Now we're going to be measuring this at 6 different places, just below each apex seal and between each apex seal. Simply take a micrometer and place it between the 2 thrust surfaces. Take your reading. Now, we'll take this measurement and compare it against the maximum rotor housing width, and that will give you your rotor running clearance, which needs to be about 0.010 of an inch or 0.005 of an inch on either side. If for some reason your measurements vary drastically between locations, your stationary gear could have backed out. And you can reseat it by taking a plastic hammer and striking it several times around the perimeter. Now do a visual inspection of the bearing, looking for areas of extreme wear or damage. Remember that this long strip that has no babbitt on it is actually the joint of the bearing, and it was ground down flush to eliminate any high spots by the factory. This is considered normal. We're going to measure the rotor bearing diameter. We're going to do this exactly the same way that we did the main bearing and the stationary gear. We'll divide the bearing into 2 halves, the bottom half and the top half, divided by the oil groove. Now, you'll be measuring 2 measurements for each half, horizontally and vertically, horizontally and vertically. Please make sure that you do not measure on top of the rotor bearing joint. That could give you an erroneous reading. With all the rotor seals and springs properly cleaned, let's turn our attention to inspecting them. Checking the free height of the apex seal springs. Take the apex seal spring and flip it over so it stands up. Then take a dial caliper and measure directly at the center. The small spring maximum height should be 130 thousandths. The minimum height should be 67 thousandths. This one is 127, so it's fine. The measurement procedure is the same for the large spring. The large spring height, or maximum height, should be
246 thousandths, and the minimum height should be 181 thousandths. This one is 210, so it's fine as well. If the apex seal springs fall below the minimum height, I have been successful in re-arcing them, and you can re-arc them slightly by putting your thumbs in the middle of the spring and your pointer fingers on the outside and bending slightly until the spring gives, and then rechecking your free height. Now inspect the rotor oil seal springs for any type of excessive wear or damage. Check the bent ends of each oil seal spring. There's a square end and then there's a curved end. Make sure that these are bent up at least 45 degrees from the leading flat. If they've been mashed a little bit, take a pair of pliers and bend them back up about 45 degrees from this leading flat. With the rotor oil seals facing right side up, that's the round tab facing down and the rectangular tab facing up, you'll notice that we have two opposite sets of springs. Those with the rectangular tabs facing the right, those with the rectangular tabs facing the left. These tabs keep the rotor oil seals from rotating in their bores. It's very important that you put the correct spring set in the correct rotor face. If you've mixed them up, this is the way they go. The front rotor open side gets the rectangular tabs that point to the left. The front rotor gear side gets the rectangular tabs that point to the right. The rear rotor open side gets the rectangular tabs that point to the right, and the rear rotor gear side get the rectangular tabs that point to the left. If you're reusing side seal springs, check each peak on each spring to make sure it has not worn flat and in danger of breaking. Also, place the springs together and make sure that they hold a uniform shape together. Inspect the corner seal springs for any type of damage or excessive flattening. They will flatten out somewhat, and they can easily be re-arced by taking them between your fingers and then just twisting. Inspect the corner seal for any significant wear or damage. You'll always find two lines, one on either side, and that's where the side seal actually comes into contact with the corner seal. That's considered normal. Now take a set of dial calipers and measure the outside diameter of the corner seal. The outside diameter should be between 432 and 433 thousandths of an inch. Flip the corner seal over on its side and measure the height. The height of the corner seal should be between 268 and 276 thousandths of an inch. Check the side seal for any significant wear or damage, especially along the running edge, which is the shiny side. Now, take your dial calipers and measure the thickness of the side seal. The thickness of the side seal should be between 26 and 27 thousandths of an inch. Flip it on its side and measure the height of the side seal. The height of the side seal should measure between 112 and 124 thousandths of an inch. The main part to inspect on the rotor oil seals is the shiny inner edge. That's what actually seals against the side housings. Inspect it carefully under a magnifying glass for any chips or gouges. Then take your dial calipers, separate the jaws by 20 thousandths of an inch. And under a magnifying glass, inspect the width of the shiny lip. If the shiny lip is excessively over 20 thousandths of an inch, then the rotor oil seal is worn out. Now we're moving to the rotor dry assembly stage. This is an inspection where we take all the rotor seals and springs, put them back in their respective sockets or grooves, and inspect the clearances between them and between their grooves and sockets. We'll begin by installing the corner seal springs. These go in with the opened end facing the apex seal groove. Just drop them in with a screwdriver and push them down until they're relatively tight against the bottom. Now take the correct corner seal and drop it into its hole. Push it down. Make sure that it moves freely up and down. Using one feeler gauge as a straight edge, See if you can slide at least a 20,000ths of an inch feeler gauge under the corner seal. That's checking the corner seal protrusion. It should be a minimum of 20,000ths of an inch. With all the corner seals in place, it's time to install the side seals and side seal springs. Make sure when you install the springs that the spring ends point up. Just drop them into place. Take the corresponding side seal. The shiny side goes up. And drop it into place. Once the side seals are installed, take a 1 3/1000 feeler gauge and inspect the clearance between the side seal and the side seal groove. You should be able to get a 1/1000 feeler gauge into the groove, but not a 3. If you get a 3 into the groove, then either the groove or the side seal is excessively worn, and you may need to replace either the rotor or the side seal. Moving to the rotor oil seals, make sure that you select the proper oil seal springs for the rotor face. This is the front rotor open face, which means it's going to have the springs that have the square ends pointing to the left. When installing the rotor oil seal springs, make sure that the round tab on the spring goes into the machined hole in the bottom of the groove. Flip the oil seals upside down and locate the 2 rectangular pockets. One of these pockets must line up with the rectangular tab on the oil seal spring when installed. So flip your oil seal right side up again, line the rectangular pocket up with the tab, and drop it into place. With the rotor oil seals installed, you need to check the free height, which is exactly the same as the corner seals. Use a large feeler gauge as a straight edge, and make sure that you can pass at least a 20,000ths feeler gauge underneath. The final dry assembly inspection is the corner seal to side seal clearance. What you want to do is take your fingers and spread them out along the side seal that you're going to be checking and pull it away from the corner seal that you're going to be checking. Take several feeler gauges and try to slide them between the side seal and the corner seal. All right, and this clearance is 4/1000ths of an inch. The minimum clearance is 2/1000ths and the maximum clearance is 16/1000ths, the minimum being better. Apex seal to apex seal groove clearance is checked by sliding a new apex seal into the groove and then taking feeler gauges and sliding them between the apex seal and the groove to determine the actual clearance. Your clearance should be between 2.5 and 6/1000ths. And this concludes rotor inspections. Calculating the running clearances for the eccentric shaft and rotors are within the realm of second-grade math, but they are important indicators as to how the engine will perform, especially in the areas of durability and efficiency. An engine that is too loose will have a hard time maintaining critical oil pressure, especially at low RPMs. They also tend to be noisy and inefficient. An engine that is too tight is very sensitive to temperature and RPM extremes. Bearing wear may actually be accelerated due to the oil's inability to carry heat away from the bearings, as well as the possibility of physical interference. Our target dimensions were chosen to give adequate clearances to handle thermal expansion and proper oil circulation, without excessive mechanical slop. Calculating the eccentric shaft oil clearance. For the main bearings, take the minimum main bearing inner diameter and subtract the maximum eccentric shaft journal diameter. Our target clearance is between 1.6 and 3.1 thousandths of an inch. For the rotor bearings, take the minimum rotor bearing inner diameter and subtract the maximum eccentric shaft lobe diameter. Again, our target clearance should be between 1.6 and 3.1 thousandths of an inch. Rotor running clearance. Take the rotor housing minimum width and subtract the rotor maximum width. That'll give you your running clearance. Our target values are 4.7 to 10 thousandths of an inch.
Rotaries have been used in several power applications, from stern drives to aircraft. Its high power-to-weight ratio makes it an attractive candidate for off-road applications. In this section, I'll cover some modifications that will enhance the 13B's reliability and power, with the emphasis on reliability. Before we begin, let's take a ride in a highly modified rotary-powered vehicle.
Hey, they're prop.
Disabling the oil bypass thermostat. This is the oil bypass thermostat. The oil bypass thermostat is a device that was first used in 86 and on rotaries. Its purpose is to divert cooling oil away from the rotor jets on initial startup, to speed up warm-up times and allow the engine's emission systems to come online faster. There are two drawbacks to this device. The most obvious is that if it fails, your engine will simply burn up because of overheated rotors. The second problem is that its reaction time can sometimes be slower than necessary, causing the rotor oil seals to be burned. This will cause smoking and excessive oil consumption. To disable the bypass thermostat, take a pair of pliers and remove the actuating rod or piston. Now we need to modify the front eccentric shaft bolt to hold the bypass thermostat in its closed position. Find a spare bolt that will fit smoothly into the hole of the eccentric shaft bolt. I'm using an extra front cover bolt.
Take your bolt and cut about a 1/2 inch section off of it. Chuck the stub of the bolt up in a drill and then spin it against the grinding wheel to make sure that it's flat. Chamfer the edges slightly. Take your front eccentric shaft bolt and your vernier calipers and measure the depth of the hole in the bolt. This one is 0.825 or 0.826. The goal is to reduce the depth by 4/10 of an inch. So drop your plug in the hole and measure it again. Our target is 0.425. 426, and right now we're at 0.340. So we've got a little bit more than 1/10 of an inch to grind off of our plug to get to our target hole depth. And just continue to grind on the plug until you get to your target hole depth. In other words, you're reducing the depth of the hole by 4/10 of an inch. After several grinding procedures, I've gotten the depth of the hole reduced to 0.429. which is basically 3/1000ths of an inch off target, which plus or minus 50/1000ths of an inch really won't bother you. At this point, this is what we want. The next step is to apply just a little dab of epoxy to one end of the stub and then install it in the eccentric shaft bolt. Let me review what I've done. First of all, I removed the actuating rod or piston from the thermostat, disabling it. Then I shimmed up the hole in the front eccentric shaft bolt. This pushes the thermostat back into its closed position, turning on the oil jets for the rotors. Therefore, the oil jets are on at all times regardless of the oil temperature. And this is the way that pre-86 rotary engines were set up to begin with. Therefore, your engine does not have to depend on this thermostat working to survive.
Solving oil main O-ring problems. Now this modification is for those of us building 86 through 88 engines. The rest of you can take a coffee break. This is the oil main crossover point between the front housing and the front cover. There is a combination O-ring and gasket used to seal this junction. This area has often been troublesome to seal in high-power, high RPM applications. Not only is it where the oil pressure is at its highest, being before the first pressure regulator, but the gasket supplied by Mazda is slightly thicker than the original. The O-ring is not crushed completely and therefore fails. There are two simple remedies. Both include omitting the front cover gasket. The first and permanent fix is to take a .650 end mill and mill the O-ring seat approximately 20/1000ths of an inch to compensate for the omission of the front cover gasket. The factory O-ring is used and RTV sealant is substituted in place of the gasket. The second fix is a little Neanderthal but equally effective. Place the O-ring inside a washer and sand it down approximately 20/1000ths of an inch from its free thickness. Use a piece of 400 wet or dry lubricated with WD-40. Be careful not to sand your fingers. In both cases, I recommend making a standpipe out of 200/1000ths OD steel tubing. This is installed in the front housing where the oil metering pump line crosses over to the front cover. The matching hole in the front cover is slightly larger, so the standpipe is a press fit in the front housing and a slit fit in the front cover. This keeps the RTV from squeezing into the crossover and blocking the oil's path to the metering pump. Place a light coat of RTV around the outer perimeter of the front cover. Do not put any RTV over the oil main crossover. Then install it in a normal fashion. Increasing cooling oil flow to the rotors.
Here's a modification straight out of the Racing Beat catalog. If you're running your 13B at high RPMs, high loads for extended periods of time, then you may want to increase the oil flow to the rotors. Now the way you do that is you remove the eccentric shaft jets, springs, and check balls. You omit the check balls and springs, and in their place you press in a number 200 Weber jet. Now this decreases the overall size of the eccentric shaft jet, but since you've removed the check ball and spring, the restriction has been reduced, so the overall oil flow increases. First thing you do is you take your jet and you run it along the side of a file to roughen up the outer diameter so the epoxy will have something to stick to. Now this is an extra precaution. Racing Beat just simply presses them into place. I like to add a little dab of epoxy to ensure that they're going to stay there. I'm going to take a lacquer thinner soaked rag and wipe the jets down to make sure they're completely degreased. I'll do the same thing with the eccentric shaft jets. Now simply take the jet, get it started like that, and press it all the way in. Press it in place. After mixing up a little bit of epoxy, take your new jets and apply just a little bit of epoxy down in the groove of the eccentric shaft jet. Make sure you don't get it in the threads. clean this one up a little bit. This is just a little bit of extra insurance to make sure that jet doesn't come loose, even though my fingers are still hurting from pressing them in. Now I'll go clean the excess off, and that'll be ready to go. And this is what the oil jets look like when the modification is complete. Now, simply reinstall them in the eccentric shaft, omitting the check ball and spring, and don't forget the blue Loctite on the threads.
Installing a distributor in the 13B.
Installing the early model 13B and 12A distributor in the 86 through 92 13B. This is a popular modification if you plan to convert to carburation. It is possible to keep the current distributorless system, but this takes a considerable amount of time to make the bracketry for the throttle position sensor, and it still leaves you with an unadjustable ignition curve. Installation is very simple. The distributor is simply dropped in, then a simple harness is made to supply power to the ignition modules and then to the coils. There are two models of the distributors. One has the ignition modules mounted remotely, and the other has them mounted on the distributor body. I prefer the remote style, as pictured, because it lends itself to more modification.
In conjunction with installing the distributor, I like to substitute GM-style ignition modules in place of the stock Mitsubishi units. There are several advantages to this, including price and availability. An aftermarket GM ignition module can be purchased at almost any auto parts store for $15 to $25, whereas the Mitsubishi units are hard to find and can cost more than $150. There's also power. The GM ignition module saturates the coil at 5 amps of current, which is more than 3/4 of an amp above the stock unit. This, with aftermarket coils, translate into a hotter spark, which is a benefit to the Rotary. If you need a wiring diagram to make this work, send me a self-addressed stamped envelope and I'll give you a copy. A killer parts combo for the 6 ports. The killer parts combo parts combination. I know this sounds like a McDonald's lunch special, but actually it's a great combination of parts that will wake up any 13B 6-port, especially the 86 through 88 models. The first ingredients are the rotors. These are 89 through 92 rotors. They feature almost half a point increase in compression, with the added benefit of being almost half a pound lighter than the 86 through 88 units. Since the rotors are lighter, they change the internal balance of the engine. Therefore, you must run the corresponding 89 through 92 front counterweight and flywheel. The next secret is to substitute an 87 through 92 Turbo 2 intermediate housing. This is like an instant port job. The one drawback for 86 through 88 engines is that you must plug the rectangular heat riser with epoxy, as the 86 through 88 engine intakes will not cover it. 89 through 92 users do not have to worry about this since their intake is designed for this heat riser. And finally are the rotor housings. These are 87 through 91 Turbo 2 housings. Turbo 2 rotor housings do not have the exhaust port divider, promoting better flow into the header. Remember to use the Turbo 2 O-rings in the water jacket port behind the intake to ensure a proper seal. Remember, whatever flows into an engine must also come out. Without a high-flow exhaust system, these parts will do little to improve performance on their own. Contouring the secondary ports on the 13B 6-port. This modification is applicable to engines that will be operating under moderate to high load conditions and do not require gobs of off-the-line torque. An example for this modification would be an airplane. The secondary port and its shutter valve do not have the most efficient flow path for the air and fuel to follow it. It must make a sharp 90-degree turn in order to enter the rotor housing. Again, where applications that do not require lots of bottom-end torque, this mod can increase the efficiency of the port. Begin with a clean, degreased side housing. Take an air grinder with a sanding roll or stone and roughen up the area to be contoured. Then take a rag soaked in lacquer thinner and degrease the port one last time. Cover the face of the housing with duct tape to avoid getting epoxy on it. Cut out the outline of the port. Use a high grade of epoxy putty that is both fuel resistant and rated for temperatures above 200 degrees. Mix small balls of putty and apply them in layers. Apply some lacquer thinner with the tip of your finger to help smooth the putty. And keep applying layers till you have it built up to the right height. If you take your time, you can finish the port without having to sand it. Now go ahead and remove the tape and clean the area up. And this port is finished. Here are some shots of the recontoured port.